Assalamualaikum, we are from Group 4D. We want to present our session about chromatography in applications in food industry to determine vitamin in beverages. So these are our group members, which is we have me, I am Wanaras Putri binti Wanasi, we have Nurjana, we have Nurhanan, and we have Siti Nur Aisyah. This is Wanaras Putri binti Wanasi. So I will continue about introduction. What is chromatography? Chromatography is a process for separating components of mixtures. To commit the process, the mixture is dissolved in a substance called the mobile phase and passes through second substance called the stationary phase. Different components of the mixture pass through the stationary phase at different velocities and separate from each other. The properties of the particular mobile and stationary phases determine which materials move faster or slower and how they are separated. These different equation times are called inhabit times. Next is theoretical. This chromatography can be used in food industry applications. For example, determine the content of food or drinks, such as determine the drugs or vitamins. Specifically, we determine vitamins in drinks only, such as determine vitamin A in milk and determine vitamin C in orange juice. There are ways that we can use in this chromatography to determine the content. One of the ways we use is thin layer chromatography.
Thin layer chromatography is one of the simplest, fastest, and least expensive chromatographic technique used to separate organic compound and test compound purity for qualitative and quantitative analysis. TLC is used in pharmaceutical and drugs, clinical chemistry, forensic chemistry and biochemistry, cosmetology, food analysis, environmental analysis, and analysis of inorganic substances. The principles of TLC are: the component with more affinity towards stationary phase travels slower, while component with less affinity towards stationary phase travel faster. Determination of vitamin C in fruit juice. When a product of vitamin C content is advertised as a feature, it is necessary to conduct quantitative measurement of ascorbic acid. This determination is a regulatory requirement because ascorbic acid is an extraneous substance. In this determination, the materials used are chloroform, ethyl acetate, acetic acid, oxalic acid, ascorbic acid, and others. Procedure to determine vitamin C in fruit juice. Pipette 2 ml fruit juice into a measuring flask. Add 25 ml of 4% oxalic acid solution. Add 2 ml of 0.5% aqueous dichlorophenol indophenol solution. Add 10 mg Tyra. Fill up with water until 100 ml. Transfer 20 ml into a 50 ml centrifuge vessel and add 4 ml of the 2% solution of 2,4-dinitrophenyl hydrazine in 70% sulfuric acid. Extract the hydrazine with 3 times 6 ml ethyl acetate. Lastly, apply the orange color extract directly onto the HPTLC layer. The second experiment, measuring vitamin A and D in milk. Vitamin A is used to fortify low-fat and skim milk, while vitamin D is used in fortification of whole, low-fat and skim milk. The objective of this experiment is to develop a method for measuring vitamin A and D in milk. The current method of analysis for vitamin A listed by the AOAC is the car-price colorimetric method. The use of gas chromatography for vitamin A analysis. The study concluded that vitamin A decomposed, so gas chromatography was unsatisfactory. For vitamin D, the biopsy method was used, which are time-consuming and expensive. Colorimetric method also used for quantifying vitamin D, which requires sample with larger amount of vitamin D than are in milk and extensive cleanup prior to analysis for accurate result. The materials used in determination of vitamin D3 in whole milk: acidified ethanol solution (HCl) solution, saturated sodium chloride solution, methanolic potassium hydroxide solution, vitamin D3 standard solution, vitamin D2 standard solution, vitamin A palmitate standard solution, butylated hydroxytoluene solution, preparative thin layer chromatography plates, liquid chromatographic system, chromatographic columns, guard column, and microfilter apparatus. The first procedure is extraction of the lipid material. A 250 ml polypropylene centrifuge bottle was filled with a 50 ml sample of commercially homogenized whole milk. In order to determine recovery, a known quantity of vitamin D3 standard was added to some sample. The centrifuge bottle was then filled with 5 ml of saturated NaCl solution, 90 ml of acidified ethanol, and 50 ml of hexane. The bottle was shaken for 20 minutes at 300 rpm on a orbital shaker. After that, the milk solution was centrifuged in a refrigerator at 4 degrees Celsius for 20 minutes at 6000 rpm. As a result, two distinct layers were formed. The second procedure is alcoholysis. 8 ml of KOH was added after the hexane layer was decanted into a 250 ml Erlenmeyer flask. After a gentle shake and about 2 minutes of standing, 2 volumes of HPLC grade water were added to the flask. The mixture was gently stirred in the flask before being poured into a separatory funnel of 250 ml and allowed to stand for approximately 5 minutes until the upper hexane layer was removed. The hexane was slowly decanted into a 500 ml round bottom flask with a standard taper joint after the water phase was slowly removed from the separatory funnel. A rotary flash evaporator at 60 degrees Celsius and 100 ml used to evaporate hexane. Once the flask had been rinsed twice with about 5 ml of hexane, the methyl ester were added to a 20 ml screw cap valve. Esters were either immediately chromatographed on a TLC plate or sealed and stored at 40 degrees Celsius for subsequent analysis. At this point, a desiccator was used to cool a TLC plate to room temperature after it was heated for 1 hour at 140 degrees Celsius in an oven. Using a disposable pastil-type pipette, the methyl ester sample was applied 2 cm above the bottom of the plate. A small amount of vitamin D standard solution was applied to a portion of the application line that was left free of esters, roughly in the middle of the plate. Esters were applied in thin layer, allowing the previous layer to almost dry before applying the next one. The vial was then applied to the plate after being rinsed with 10 to 15 drops of hexane. The plate was developed in a glass tank with chromatographic paper lining the side and a water-soluble gel sealing the top, hexane, and a developing solvent mixture. The vitamin D was found by inspecting the plate under short wavelength ultraviolet light 254 nanometer. When the solvent reached the plate top, a second tank with hexane contained a second partial development. When the solvent reached the top of the well-known standard vitamin D spot, the plate was taken off. The vitamin D in the sample was located on the plate by viewing it under a short wavelength UV light as before after the plate was allowed to completely dry. Next, determination of vitamin A palmitate in non-fat milk. Except as noted, the methods used to determine vitamin A palmitate in non-fat milk were the same as for vitamin D. Firstly, in extraction of the lipid material, a known quantity of vitamin A palmitate and 1 ml of a BHT solution containing 1% were added to a commercial non-fat milk sample of 50 ml. Second, in alcoholysis, in place of hexane, HPLC acetone was used to rinse the rotary evaporator flask. And lastly, in chromatography, The chromatographic condition that distinguishes from the vitamin D procedure is solvent for HPLC substitution for methanol.
Assalamualaikum, my name is Nurjana binti Sufyan and I will continue with the example of result. Food industrial use of TLC can determine the percentage of the vitamin A and D in milk. The mean corrected recovery of the vitamin D was 94% with coefficient of variation ranging from 2.5 to 5.3%. The analysis for vitamin A palmitate in non-fat milk utilized the same basic procedure except for elimination of thin layer chromatography. Mean recovery of vitamin A palmitate was 99% with coefficient of variation 3.2 to 10%. So this is the table of result for vitamin A and D in milk. The result for vitamin C in orange juice from this TLC is the RF value for ascorbic acid, which is 0.4. And that's all from me. Thank you.
Analysis method for vitamins A and D in milk enables sensitive, accurate, and quick quantification. Both vitamins had corrected mean recoveries more than 90% with detection limits of 1.0 times 10 to the power of negative 9 gram over 10 sample for vitamin D and 1.3 times 10 to the power of negative 9 gram sample for vitamin A palmitate. The methods are straightforward. The examination of whole milk for vitamin D took around 8 hours, whereas the study of non-fat milk for vitamin A took about 3 hours. The main benefit of this process over others is that it uses alcoholysis instead of saponification. Alcoholysis allows faster analysis and a gentler process with less possibility for vitamin damage than saponification. The vitamin C content of fruit juice and similar goods is advertised. Quantitative testing for ascorbic acid is required. Vitamin C is converted to dehydroascorbic acid by mild oxidation. This is subsequently isolated from matrix components by TLC and measured densitometrically by absorbance at 510 nanometer as its for the nitrophenyl hydrazone derivative. The methodologies used in this study have the potential to be used for qualitative analysis of vitamin C in fruits.